I usually pick topics based on what stops me in my tracks. Something so strange or beautiful, I have to pause just to take it in. This was one of those moments. You see, we're told the universe has a speed limit. Nothing outruns light. Not a rocket, not a signal, not even gravity. It's one of the most fundamental rules in all of physics. So imagine my surprise when I found something that didn't fit. Some galaxies are moving away from us so fast that their light cannot catch up. And I thought, wait, if light is the fastest thing there is, how can anything, even space, get ahead of it? That's what this episode explores. We'll walk through the standard explanation, why this doesn't break relativity, and how physicists think about expansion. But I'll be honest, after writing this whole script, I hit something deeper. What is this thing that can outrun light? I hope you'll stay with me to the end because the more I looked into it, quite honestly, the stranger it got. But to attempt to understand what's going on, we need to pause and get clear on two things. What does it actually mean for space to expand? And even more fundamentally, what do we mean by space? At least according to our current best understanding. We'll start with the first. The universe is not expanding like an explosion, with galaxies flying outward from some central point. In fact, there is no center. The expansion is happening everywhere, and what's growing isn't the speed of the galaxies, but the space between them. You can imagine space as an invisible cosmic grid, a flexible framework that defines distance across the universe. Over time, that grid stretches. The galaxies themselves aren't racing outward. They're more or less staying where they are in space. It's the grid, the fabric between them that expands. This idea comes from general relativity, which tells us space and time are not fixed backgrounds. They're dynamic, shaped by energy, matter, and the structure of the universe itself. To describe this mathematically, physicists use something called the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW metric for short. This model describes a universe that's smooth and uniform at large scales, and it includes a crucial quantity called the scale factor. The scale factor is a number that tells us how much space has stretched over time. You can think of it as a kind of cosmic ruler, one that expands as the universe evolves. If the scale factor doubles, so does the distance between any two unbound objects. Unbound objects are things not held together by gravity, like distant galaxies drifting far beyond each other's influence. And this change in the scale factor is not just abstract. It's something we can actually observe. As space stretches, the light traveling through it stretches too. That's what we call the cosmic redshift, a shift in the wavelength of light as space itself expands. So when scientists say the universe is expanding, they mean that this cosmic ruler, the scale factor, is increasing. And when it increases fast enough, even galaxies can begin to recede from each other faster than the speed of light. Now let's turn to that second question. What are we actually calling space, at least as far as we currently understand it? We all picture it differently. Some imagine it as a void, others as a container. But in physics, space isn't just a place where things happen. It's what allows anything to have position, direction, or distance in the first place. In Newton's time, space was treated as a fixed, invisible grid, a kind of stage that existed whether or not anything stood on it. Then Einstein came along and changed that picture. In general relativity, space and time are not static. They're woven together into a single flexible entity called space-time, a fabric that bends in the presence of mass and energy. It can ripple, it can stretch, and it can evolve. A planet doesn't orbit because it's being pulled. It follows a curved path through distorted space-time. But even that is not the full story, because on the quantum level, space is never truly empty. Even in a perfect vacuum, fields fluctuate. Virtual particles flicker in and out of existence. Tiny bursts of energy flash and vanish. This is what physicists call the quantum vacuum, the lowest energy state of space. So space is not just a geometric fabric, it's also full of fluctuations, alive with uncertainty and motion, even at its quietest. But it gets stranger. Some physicists theorize that space itself might not be fundamental. In a framework called the Anti-de Sitter Conformal Field Theory, or ADS-CFT, the geometry of space can emerge from patterns of quantum entanglement, as if distance itself is just a reflection of how connected two things are. In loop quantum gravity, space is made of discrete loops of information, like atoms of geometry woven into the illusion of smoothness. And in causal set theory, space is not continuous at all. It's a network of events structured only by cause and effect, with no backdrop underneath. In these models, space is not a substance. It isn't even a place. It's a consequence, a large-scale pattern that arises from something deeper. Maybe space is not something we move through, but something that emerges when relationships unfold. So, what are we actually calling space? Well, for the purpose of this video, it's not an object, not a void, but a structured field of possibility, a kind of geometry that gives shape to everything else. It's like a musical scale that allows melodies to exist, or a blank page that allows writing to happen. Space is not what we see. It's what lets anything be seen. And even if we're not sure exactly what space really is, we can work with it as a dynamic fabric that defines position, allows structure, and carries the unfolding shape of the universe. And somehow, it's this fabric, this thing we don't fully understand, that's said to expand faster than light. And that's where things get even weirder. So if galaxies are receding from us faster than the speed of light, doesn't that break Einstein's rule? Surprisingly, no. And the key is understanding where relativity applies. Einstein's speed limit only governs local motion, the speed at which one object can move through space relative to another. But when we're talking about galaxies on opposite sides of the observable universe, they're not racing through space. It's the space between them that's stretching, and relativity says nothing about how fast space itself can expand, and that is why this strange behavior does not violate the rules. Here's a helpful way to picture it. Imagine ants crawling on a balloon. They can only move as fast as their tiny little legs will carry them, but if this balloon inflates, the distance between them can grow much faster without any ants breaking its speed limit. So the same is true in our universe. Space can stretch at any rate, especially over vast distances, because that stretching is not motion through space. It's a change in the geometry of space itself. That stretching has some surprising consequences for what we can observe. This is where cosmic horizons come in. There is a boundary called the Hubble radius, the distance beyond which galaxies appear to recede faster than light. But that does not mean they've vanished. Light they emitted long ago might still be reaching us, even as their current positions drift farther and farther away. There's also the particle horizon, the outermost edge of the observable universe. This does not occur because of some wall or barrier, but because light from beyond that distance simply has not had enough time to reach us. It's the ultimate limit set by the age of the universe itself. Together, these horizons shape what we can see. They reflect the fact that space itself can expand faster than light. So relativity still holds, but the fabric it describes is free to stretch. The universe is expanding. Why don't we feel it? Why aren't atoms being stretched? The answer lies in what physicists call bound systems, structures held together by forces stronger than the pull of cosmic expansion. Take molecules. They're held together by the electromagnetic force, far stronger than the gentle stretching of space. The same goes for atomic nuclei, bound by the strong nuclear force. Even entire galaxies are held together by gravity, their mutual pull enough to resist expansion on local scales. So only objects that are unbound, far enough apart that there's no significant force connecting them, will drift apart as space stretches between them. Here's a metaphor that helps even if you're not a fan of raisins. Imagine baking a loaf of raisin bread. As the dough rises, it expands, stretching the space between the raisins. But the raisins themselves don't grow. They hold their shape, thanks to the strong forces within them. In this case, the dough is space, and only the distance between the raisins or unbound galaxies are growing. So in summary, why don't we feel it? It's because the expansion of space is incredibly subtle on small scales, completely overwhelmed by the forces that bind matter together. Still raises an enticing question, however. If expansion only becomes visible across vast distances, could it ever happen in reverse? Could space collapse or expand wildly inside a black hole? That's a story for another video. But it points to the fact that something deeper is clearly unfolding. For now, though, let's turn to what we can observe. Before we go further, let's pause for a moment. I understand from many of you and my own research that there are real critiques of our current cosmological model, and those critiques matter. The alternative models provide some genuinely thought-provoking publications that challenge the standard picture. We are not exploring all of those here, but if you want a future episode diving into some of the alternative theories, let me know in the comments. Still, here's what we do observe in the standard model. Light from distant galaxies is redshifted. We mentioned this earlier. This is where the wavelength is stretched toward the red end of the spectrum. And the farther away a galaxy is, the more stretched that light becomes. This is exactly what is expected if space itself is expanding. And it lines up with something called Hubble's law, a relationship between a galaxy's redshift and its distance from us. So far, it fits with the idea that galaxies are not racing through space, but that the space between us is growing. Then there's the cosmic microwave background, or CMB, a faint, nearly uniform glow of microwave radiation that fills the entire sky and reaches us from every direction. According to the standard model, the CMB is a relic from about 380,000 years after the Big Bang, a snapshot from an era called recombination, when the early universe cooled enough for electrons and protons to form neutral hydrogen atoms. That shift allowed light to travel freely for the first time, a process known as photon decoupling. From that moment on, photons could move through space unimpeded, and some of that ancient light is still reaching us today. While there are still puzzles in how we interpret the data, the CMB does remain one powerful piece of the evidence for an expanding, evolving universe. Taken together, the redshifts we observe, the motion of galaxies, and the background light left over from the early universe, they all support the idea that space itself can not only stretch, but is stretching. And more than that, though, this stretching seems to be speeding up, which brings us to the next big question. What's actually powering the expansion? What's driving it? When astronomers discovered the universe's expansion was accelerating, they had a problem. That behavior did not fit existing models. To account for it, physicists proposed something new, a kind of repulsive force. They called it dark energy. To be clear, it was not necessarily a direct discovery. In fact, we're still looking for it, but it was an inference, something that must exist based on how the universe behaves. The simplest explanation is that it's a property of space itself. If space contains energy, then the more space there is, the more energy you get. And if that energy creates pressure, it can drive space to expand even faster. This is the idea behind the cosmological constant, a term Einstein once added to his equations, later dismissed, and then was revived by modern cosmology. In this view, space has a baseline energy, even when it is empty. As more space appears, more energy emerges, pushing the expansion to accelerate. But that's only one possibility. Some researchers propose a dynamic explanation, a field that changes over time and space, called quintessence, a term from ancient philosophy now used to describe a hypothetical energy that varies across the cosmos, much like a shifting wind. Other ideas go even further. One theory called entropic gravity suggests that gravity, and perhaps expansion itself, emerges from the thermodynamics of information. In that view, the cosmos isn't shaped by a force, but by how information is organized and exchanged across space and time. So as you can see, this field is still developing. We don't yet know what dark energy is, and maybe there is an alternative explanation. For now, I think of dark energy as a placeholder, backed by equations and some evidence, but still wrapped in mystery. We've explored what space is, how it expands, and why that expansion can outpace light to the best of our current understanding, all without breaking the rules of relativity. We looked at redshift, cosmic horizons, dark energy, and the vacuum itself. We looked at alternative theories that offer promise in another way to look at it all. But now let's take a step back. If space can expand faster than light, maybe the deeper mystery isn't how fast it stretches, but what space actually is. At one level, space is geometric. There's no doubt about it, defined by curvature, distance, and dimension. At another, though, it's quantum, flickering with uncertainty and fluctuation. And maybe, at its root, space is informational, emerging from patterns, entanglement, or correlations we don't yet understand. In that case, space might not be a substance at all. It might be a type of story, a way the universe arranges connection and form. And yet, this unseen structure defines what can happen, where it can happen, and when. It carries the expansion of the cosmos. It lets physics unfold. We live inside something that outruns light, something that bends, ripples, and maybe isn't fundamental at all. We call it space, but do we really know what it is? Next time you look up at the stars, remember, what separates them may be as strange as what binds them. Thank you so much for your time. I cannot wait to read what you think about everything. Share your thoughts with me and the community below in the comments. If you come across any piece of science, something lesser known, that you think deserves a spotlight, send me an email or drop it in the comments as well. If you're new here, welcome. Please join Bioillumination, subscribe. Everyone like this video, but most importantly, until next time, take care.